So I wanted to go back to Lagrange's theorem, which is what I was talking about non-technically in the first clip from this chapter, and look at it again, this time sort of the 3D version instead of the 2D version. So here's the actual statement of Lagrange's theorem. If we have a function with a constrained extremum at a point that's located on the level surface of some other function, so that's what we're using as our constraint set. So if we just restrict to looking at the values of f on this level surface, then its maximum occurs, or minimum occurs, at p naught. Then it has to be the case that the gradients of f and g are parallel at that location. So for this example, I'm imagining that S is this level surface right here. Looks like it's given by a level set of the function x squared plus y squared plus z squared. So maybe S is the level set where G takes the value 1. So that would be the unit sphere. Okay. And we can think of this as being the surface of the sun for sake of illustration. And so the function f that I'm interested in is that f is going to be the temperature at a given point in space. Okay, so there's temperature all over the place. For this example, I'm just restricting to the surface of the sphere. So I've colored it accordingly, and with my color scheme, we've got minima happening where it's yellow, and then there's maxima happening where it's dark red. Okay, so suppose we have a point on this surface, so here's our p naught, where f takes a value, or an extreme value. Okay, then take a look at this and notice that if we look at a level, where a level surface of f intersects the sphere, it would be something like this. So you could imagine that the other points in space where f takes this value, maybe they're on this plane kind of here. And then as the temperature increases, maybe we move a little bit inward, then that's going to correspond to, you know, some surface. Maybe f takes the same values everywhere on this surface here, and so on and so forth. And as these are moving outward, what we have is we see that f is increasing as we go outward, right? And so maybe I'll clear up this picture just a little bit by erasing some of the extra junk, and we can take this idea that f is increasing as you go that way, and you can see that the very last of those surfaces I drew that touches the sphere is going to be the one that's tangent to it at exactly that particular point. So that kind of gives it away. What we have is that the level surface of f is tangent to the, well, this tangent to s, and s, which is the level surface of g. Okay, so when I say that the level surfaces are tangent to each other, I actually mean that the tangent plane to the level surface of f and the tangent plane to the level surface of g are parallel. And so if we have two planes that are parallel, then that means that their normal vectors are also going to be parallel. And the normal vectors are given by the gradients. So that tells us that the gradient of f at p naught is parallel to the gradient of g at p naught. And the equation form of that statement is that one is a scalar multiple of the other. And so that's where we get this formula for the Lagrange multipliers. By the way, lambda itself is the actual multiplier.